All right, for those of you working through learning target number 9, I wanted to go over for you number 2 on the worksheet because there was an error from the Oxford book. So when I get a chance, I'll email Oxford again and say the answer's wrong. This is the wrong answer, and I want to show you why. So this problem says 2 moles of SO2, 1 mole of O2 are mixed in a 3-liter sealed container, and the system is allowed to come to equilibrium. The conversion rate of sulfur dioxide to sulfur trioxide is 15%. Calculate the equilibrium constant for this reaction. So where they messed up in the book is they forgot they had a 3-liter container. So I've got to find my initial concentrations for all of these first. I'm going to do SO2 first. And SO2 had 2 moles over a volume of 3 decimeter cubed, and I'm going to round that to 2 sig figs and say 0.067 moles per liter. Concentration of oxygen is going to be N over V again. It's going to be 1.4 over 3. When I do 1.4 over 3, I get, with 2 sig figs, 0.47 mole per liter. And I have no SO3 to start. Now, another tricky piece here is I said that the conversion rate of SO2 to SO3 is 15%. That means that 15% of this is converted into this. So I'm going to say 0.67 times 15%, or 0.15. And I'm going to find that conversion rate is 0.10 mole per liter. And so at equilibrium, I'm going to end up with 0.10 mole per liter of my SO3. So now I'm going to fill in the rest of my ice table. Using the coefficients in my balanced chemical equation, I'm going to shift to the right, so I'm going to decrease the amount of SO2 by 2 moles proportionally. I'm going to decrease the amount of O2 by some amount proportional to 1, and I'm going to increase the SO3 proportional to 2. This piece here has now gotten me enough information to get what that change will be. So I can say 2x equals 0.10. So essentially dividing that in half, I'm going to get 0.050 for my change. So if I'm going down here, this will be 0.47 minus 0.050. I will find that my new value here is going to be 0.42 moles per liter. And then this one here is going to be 0.67 minus 2 times 0.050. 0.050 times 2. And then I'm going to subtract 0.67 minus that. And I'm going to get this to be 0.57 moles per liter. Now I've got all the information I need to find my K value. I'm going to erase so I can have some more space here. So again, the book did this and left this at 1 mole per liter. That was incorrect. Bad Oxford. So K is going to be the concentration of SO3 squared over concentration of SO2 squared, concentration of O2, which gets me 0.10 squared minus 0.57 squared times 0.42. Throwing all of that into my calculator. And I find it's close to what the answer should be in the book, but not exactly. It should be 0.073. I'm going to look at units now. So with my units, I'll see here that this is going to be a moles per liter squared. This is going to be a moles per liter squared. This is going to be a moles per liter. So the moles per liter squared cancels out, leaving me with a 1 on the top, 1 on the numerator. So it's going to be 0.073, oops, 1 over moles over liters, otherwise known as 0.073 liters over moles. All right, so the answer was slightly incorrect there, but hopefully this has clarified how this problem works.